Okay, so model diagnostic. Why do we really need model diagnostic in regression analysis? So at the very first place, when we are learning regression analysis, we came across a couple of assumptions, model assumptions. To make a regression valid, it should meet a couple of assumptions. The residuals or the errors should be normally distributed. The observations should be independent, right? And the error normality, the error variance should be constant. The mean of error should be 0. So a couple of assumptions like that. True that we use a regression ANOVA method, or we used hypothesis testing after fitting the regression, and we checked the R squared, how well our regression model fit our data, things like that. But still, we have to really check whether our regression model, the fitted regression model, is valid enough to be used. So how do we check the validity? We have to check whether our regression model, the fitted regression model, really meets all those assumptions. So after fitting the model, we have to see a diagnostic plot. So that is what you call model diagnostic, right? We have to look at them and see whether the fitted model is usable. Because if it is invalid, if it violates at least one assumption, then the end result that we are getting out of the model cannot be guaranteed. So that is why we are talking about model diagnostic here in this. So we just revisit the normal error regression model just to give you some idea. So this is basically the regression model, the simple linear regression model that we have. So same thing, this slide has been repeated so many times. So actually the error should be independent, right? Covariance of EI and EJ means this epsilon I and epsilon J means what? Covariance means the relationship between ith and the jth error terms should be 0 for all I is not equal to j. So if we take the error of the first observation and if we take the error of the second observation, those two errors should not be correlated. That is how we check the independence of observations. So how do we get the error? True value minus the fitted value. Okay, so to if we can prove that our errors, it doesn't have to be the first error and the second error all the time. Any error, first and third, first and fourth, fourth and sixth. So between any error terms, if the covariation is 0 or the correlation is 0, the relationship between the two error terms are not significant, then we can say our observations are independent. What does it mean? The observations were not read in any timely order, right? For example, if you have a time series data, let's say you have a data set of rainfall, right? A data set of rainfall in every month, monthly data with some other factors affecting rainfall. Can you really fit a regression model? No, because it's monthly data. You're reading data one after the other, right? Yes, one can fit a regression model and see the factors affecting rainfall and all that, right? Just a hypothetical example. But when we do a model diagnostic, it will give us that the regression model is, the observations are not independent, or the residuals are not independent. Why? Because it's collected monthly. The observations have a timely order, right? So usually in regression, observation should be able to should able to be taken from any random order. It shouldn't go in a timely order, right? So that is just one example to give you some sense, make you sensible about this. Independent means there's no relationship between any two observations. So we check it by the residuals, we take the error covariance and see whether it's zero, right? And the variance of the error term is constant. Error variance should be constant at any level of x, right? And errors are normally distributed with mean zero and constant variance. So that is what this says. You can tell all these things just by one line. If you write this and say IID, independent and identically distributed, then that's it. So in normal error regression, these are the assumptions that we have. So in model diagnostic, what we are checking is whether our model, our fitted model is valid enough, is usable, that it meets all these assumptions. That's what we check here. Okay, so we have to learn a couple of terms first. Residuals and semi-studentized residuals. Don't panic with these terms. These are very easy stuff. Just the names, okay? Residuals, you know, it's just the gap between the true value, that means the observation, the response value that we read, and the fitted value. After fitting the model, what is the value of this, right? So the gap between those two will give you the error, right? And where the expected value of this is equal to this, you all know this. If the model is appropriate for the data at hand, then EI should reflect the properties of properties assumed for epsilon I in the previous node. So this is what we are basically checking. This should possess all these assumptions to make it a valid regression model. We can make use of this regression model only if it does not violate any assumption, right? So after fitting the model, that's what we are really checking. If it violates, anyway, if we find it like the errors are not independent, then we have to go back to data entry level and see whether they have been recorded in a timely manner. If that is the case, we really cannot go for a regression analysis. We have to think about something else, right? But if the variances are not constant, and if we think that errors are not normally distributed, there are a couple of remedies which we are not discussing under this course. But for example, if the residuals are not normally distributed, we go back to our very first data set and we do transformations for our response variable. That is just one thing. We take the log scale, right? And the interpretations change accordingly. If the variance is not constant, we just look at that particular diagnostic plot and we can come into assumptions. Okay, this particular model is not linear, so that we have to fit a non-linear model. So likewise, we can extend our regression model in a way that it meets all the assumptions. But if the error variance is, the errors are independent, errors are not independent, we cannot go for regression, right? If these two happen, we can do transformations and we can look into other way. It doesn't have to be linear all the time. There could be non-linear relationships as well, right? So we can trial and error these things and go for some model if we find something here. But what are the transformations that we are doing? How do we go for a non-linear model are not discussed under this course. Under this course, what we are discussing is the linear regression. It could be simple or it could be multiple. We didn't discuss multiple linear regression yet, which possess more than one x variables. Okay, we are going to look into that in upcoming lectures. But here we are discussing about simple linear regression, right? So within this course, we are checking whether all these three assumptions are met. If they are not met, we are not learning what to do next. But just to give you some spark, just to give you some idea, we would definitely go for transformations, right? Okay. So how are we going to check whether all the assumptions are met? Let's see. Semi-studentized residuals. So semi-studentized residuals are helpful in identifying outlying observations. Are you familiar with this word? Outliers. Outliers means the extreme cases, right? So it is defined as this EI star in notation. So basically, it's gotten by EI minus EI bar over MSE, but we know that this is the mean error, right? But we know it is 0. Okay. If you compute all these and take the mean, it should be 0, right? That is how this thing is reduced to this formula, right? So the gap between each and every error term individually together with its mean, so it's basically this one, right? Divided by root of MSE. So residuals is basically this one. Semi-studentized residuals is basically this one. If you relate this thing with the mean squared error, you should be able to identify the outlying observations. If in your data set, if you have very far away observations, cannot be accepted type of observations, so by analyzing semi-studentized residuals, you would be able to identify them. Residuals are used for examining the departures from simple linear regression model with normal errors. Yes, departure from the true observation. The gap between the true value and the fitted value is given by the residuals. Okay, so the regression function is not linear. The error term do not have constant variance. So these are the uses of residual. Okay, the error terms are not independent. There are a few outlined observations. The error terms are not normally distributed. One of few important predictors have been omitted. So this thing could be related to multiple linear regression, because here actually we are dealing with just one predictor, that is just one X variable. Okay, so this is generally given here. The use of residuals, semi-studentized residuals, everything, right? By analyzing these, you can check whether these things are happening, including this one. Okay, so linearity, if it is not linear, by looking at the residual plot, we really can get that. I'll teach you how to. Okay, if it is not linear, we cannot go for a linear regression model, right? We really cannot go for. If it does not possess a constant variant, then it violates the assumption. Still, we cannot use the fitted regression model. We have to go for some alternative in that case, right? That also could be identified by using the errors, the distribution of that, and all these things. We'll see one by one which plots should be used to identify each and every feature. Okay, diagnostic for residuals. Following plots of residuals or semi-studentized residuals. So in terms of residuals, you can use anything, even this thing or semi-studentized, you can use anything. Maybe used to identify the departures informally, right? It's not the formal way. From simple linear regression model. Plot of residuals versus predictor variable. Residuals versus X values. Okay. Plot of absolute or squared residuals. So residuals can be either positive or negative, right? If the so residuals are given by the true observation minus the fitted observation. If the true observation is greater than the fitted observation, you are getting a positive residual value, right? If it is less than, you're getting a negative residual value, right? If the observation is below your fitted regression line, that means the fitted value, you're getting a negative residual. So it has some direction. But if you take the absolute or the squared residuals, you're always getting a positive value for residuals. right? So you can either do this one or this one. Same thing you are getting, only the plot is different. But the pattern, the behavior of the plot is exactly the same, right? You can either use this one or this one, or you can go for residuals versus fitted values. Same thing will be given. I know the fitted values are for y hats, predictor variables are for x's, but still you would be getting the same pattern. You'd be getting the same outcome of by plotting all these. Same outcome in the sense, same sort of interpretation. By looking at the plot, the behavior is going to be the same. Either it is x variable or the y variable. Then again, you can look at the plot of residual versus time or the sequence. So if it shows some pattern, that means what? The observations are not independent. If it shows a pattern, it should be in random order to show that the errors are independent, which implies the response variable, the observations are independent. Plots of residuals versus omitted predictors, right? This could be discussed in multiple linear regression, because when it comes to multiple linear regression, we might be getting so many x variables. It's not always the case that you have to include all the x variables in the model. You'll learn that later on. There could be instances where you make use of only a couple of selected x variables in your model to make it predictive enough, because we always try to keep our model as simple as possible, right? Adding a lot of x variables doesn't really help. So if we have more than one x variables, more than one predictors, we can, if we omit a couple of predictors from our model, then we can plot these things and see what's happening. If it adds some significance to the model, we have to include the variable in the model. That's what it says. Box plot of residuals. So here, of course, you can identify the outliers, and by the box plot, whether it's giving you a symmetric shape or whether it is asymmetric. If the residual should be normally distributed with zero mean and constant variance, right? Anyway, if it is a normal distribution, you should be getting a symmetric box plot. What if you didn't get it? That means the residuals are not normally distributed. We don't know the mean and the variance, but at least to get some idea whether it's skewed or not. So this is also important. These are alternatives that we can go for. Normal probability plot of residuals. This is given a couple of names we are going to discuss at the end of the lecture today. QQ plot or quantile plot. I'll tell you how that's being created. This is the to check whether the residuals are normally distributed. This is the most famous way in regression analysis. We can use anything, but everybody who learns regression should be aware about this thing. Very important. Okay. Non-linearity of regression function. Okay, I said you, when we plot x and y, it doesn't have to possess a linear relationship all the time, right? Residual plot against the predictor variable or residual plot against the fitted value. I told you that these things give the same behavior, although this is x and this is y hat. Okay, is used to examine the non-linearity of the regression model. We'll see how. This can also be studied from the scatter plot, but it is not always the effective way as the residual plot. Even by looking at the scatter plot, you can see whether there's a linear relationship or a non-linear relationship. The initial scatter plot, x versus y. Okay, but usually in model diagnostic, we go for the residual plot, not the initial scatter plot between x and y. Even this can give some sort of an idea, but the most effective way is going for the residual analysis, residual plot. Okay, this is an example of non-linearity. So let's think this is our y variable and this is our x variable. Just forget about this thing. Okay, just consider this scatter plot. Okay. This is our y variable, this is our x variable. If we plot our observations, our x coordinate, y coordinate, let's say we have 1, 2, 3, 4, 5, 6, 7, 8, 8 observations in our data set. Sample size is 8. Okay, so to this x variable, when x is around 80, right? Y variable is 0 point something. Okay, when it is 100, y variable is 2. Likewise, we just have the scatter plot. Forget about this line. When looking at these scatters, can you see there is sort of a slight non-linearity between x and y? Although the scatter plots shows something slightly like this, we don't tend to go for a regression model, linear regression model, and we try to fit a line for this. Okay, generally we are trying to fit a line for this. What have we done here? The true model is non-linear, but we have fitted a linear model for this, right? Maybe the R-square is very low for this, because if the true observation is somewhere here, it's giving us a value here, right? At some places, it gives sort of the correct observation. For example, here, right, the error is minimal, right? For this sample, if we take another sample, the behavior is entirely going to be changed for this sample I'm talking about. So that's why it says here, non-linearity can be studied from the scatter plot, but it is not the advisable way, because here, by looking at this, some people really can think of this could be fitted by a line, right? It's not hardly, it's not like, it's not very tough when we talk about non-linear. It's a slight curve here. Okay, so it's not really clear by looking at this type of a thing initially. Like, we really can fit a linear model, right? So that is why after fitting a linear model, we do a residual analysis. So here they have plotted residuals versus this one, predictors, right? And can you see, so here they have done the original residuals, so there could be negatives and positives. So just see, look at this. This one is below this line. So for this particular x coordinate, this is the fitted value. So what is the residual here? True observation, 0 point something, minus the fitted observation, 1 point something. So 0 point something minus 1 point something will give you negative 1 point something. So that is this one. Did you understand how this residual plot is constructed? Just look at this one. This is a positive value. Okay, 1, 2, 3, 4. The fourth observation, 1, 2, 3, 4. It is on top of the fitted line. So yi minus yi hat, y4 minus y4 hat will give you a positive gap, right? This is let's say 4.5. Let's say this is 4. It's like no, this is 5 and this is 4. So it's just like 1, right? 5 minus 4 is 1. 5 minus 4. Okay, so it's 1. The gap between these two is positive 1. So likewise, they have plotted the gaps, the residuals for each and every x level, right? Here we can see high non-linearity. Can you see this curvature is very crucial here, right? Very serious curve could be found here, right? So by looking at this, we can exactly say the relationship between the x and y is definitely non-linear. If this is linear, these scatters should possess around this horizontal line. We should be getting a horizontal band which is very close to 0. Why? the mean of the residuals should be 0. That is also another assumption that we had. What if we have all the residuals in a line slightly with slight sparks around -1? Still, that is not a valid regression line, because in that case the mean of residuals is -1. In our assumptions, mean of residuals should be 0. Okay, so that is why we say, what is the expectation if our fitted line meets our assumption that the residuals, the average residual is 0. We don't know the distribution whether it's normal or not, but the average residual is 0, and it is a linear relationship. So we should get all these scatters around this line. We should not be getting a pattern. These scatters should be scattered randomly in a constant band. So that is the expectation, but in reality we have gotten something like this. So by looking at this plot, we can say the relationship between these two are not linear. That is what we can say by looking at this plot, right? Okay, if the linear model is appropriate, then residuals fall within a horizontal band centered around 0. Why centering around 0? Because the error variance should be mean of error, average error should be 0. On average, it should be 0, so it should be scattered somewhere around 0, and also it should be a constant band to show that it doesn't have any pattern, it's linear. Displaying no symmetric tendencies to be positive or negative. If we have a tendency, a trend line, then again it's not going to work. No symmetric tendencies. So these are the possibilities, right? So if we are getting a plot like this, always just think this is the residuals versus X plot. Residuals versus X plot. Okay. So if we are getting a plot like this, like plot A, then it is okay. Right? The model is linear and the residuals are centered around 0. They are scattered around 0. So we can say that average error is 0, but still we cannot say it's normal or not. But by this plot, we have to go for other plots as well. Right? So by this plot, what can we say? This is a linear relationship because it possesses a constant band. Constant band means what? We are getting errors like this. These scatters are going somewhere along this line, positive, negative errors. But it's going around this line symmetric. That is why we expect something like this, a constant band around 0. What if we get a plot like this? This is a cone-shaped plot, right? We can say the error variance is not constant. See, initially the error is very small. It's very close to 0. This is the 0 line, right? Initially the error is very small. When you are going, the error becomes very large. That means when you get the scatter plot, we are having scatters like this here, and when we go further, we are getting scatters here. So the variance of error, the spread of errors is not constant. This is what we can say from this plot. If we plot residuals versus X, and if we get a cone-shaped plot like this, which is increasing, what can we say? The error variance is not constant. Can you see the variability here is very low? The variance here is very high, right? It can be either the other way around, right? Initially, the variance is very high, then the variance is so. Anyway, if it is not a constant band, there should be some problem. Okay, if you get a plot like this means the errors are not independent. It possesses some trend line. Trend means with the time it increases, or with the time it decreases likewise. If you're getting something like this, or the other way around, right? This means there is a non-linear relationship, just like in this case. Okay, so by looking at the residuals versus X plot, we can come into these conclusions. So what we expect to have here is this, but we don't know. So that is why after fitting a regression line, before using that, we have to go for a residual analysis and see whether our fitted regression line is actually usable, actually valid enough to have future predictions. If you have questions, just interrupt me and ask. I'm simply moving from slide to slide. Okay, just interrupt and ask. Okay, non-consistency of an error base. So similarly, same thing, you can plot residuals and fits and tell the same thing. Residuals and fitted values, residuals and predictors, right? Anything. Variance of error term is not a constant, implying that it is a function of predictors. That is understood. Residual plots again the predictor variable, right? Or residual plot against the fitted value, residuals versus X, residuals versus fits or fitted values, is also used to examine the non-constancy of error term. If the variance of the error term is constant, then the above plots don't show any symmetric pattern, which we discussed here. It should be symmetric. If so, this can be something like this also, right? So it doesn't have to be symmetric around 0 all the time. This cone should go something like this. Still, errors are non-constant, right? Here by this plot, what can we say? The average error is approximately 0, because if we take the average here, it's 0. If we take the average here, again 0, because it's symmetric around 0. But the error variance is not constant, right? So we have to check all the assumptions. Residuals that show an increasing trend. Residuals that show a decreasing trend. Constant variance. So when we plot residuals versus fitted values or residuals versus predictors, if we get things like this, I told you here also, it doesn't have to be the increasing cone shape all the time. It could be a decreasing cone shape as well. It could be anything, right? If it is not something like this, then there is a problem. Okay, so this is when the when you increase the X variable, the residuals gets very small. But in lower range, you have a high variance, right? So they're talking about the variability here. Here, actually, the variance is either high or low or whatever it is, it's constant around the line. So this is the regression assumption, one of the regression assumptions. Plots of absolute values of residuals or the squared residuals would give you the positive residual values. So in that plot, we don't have this particular line. We don't have this line. It's starting from 0. We don't have a negative axis because the residuals are always positive, just because the y-axis is absolute residuals or the squared residuals against predictor variable or against the fitted value. Okay, just like you plotted the residuals with the predictor and the residuals with the fitted value, you still can plot the absolute residuals or the squared residuals with either of these, right? Also useful for diagnosing non-constancy of error variance. Then we are getting plots like these. So these are examples for non-constancy of error variance. right? So this shows some trend, this shows some non-linearity, right? And all these are not accepted. Only the difference is it's starting from 0. That's it. The behavior is exactly the same. If we did not square, or if we did not take the absolute value, this 0th line, the 0 axis comes somewhere here. Okay. So this is just the residual versus x, and here the absolute residual versus x. So here we are getting a cone shape, right? Here also we are getting the concept. That's why I said, although we plotted residuals against fitted values of x, or we plotted absolute residuals versus fitted value of x, or even if we plot the squared residuals versus x, we are getting the same behavior, right? Here also, what can we say? That the always look around the 0th axis, right? On the variances are not constants. A very small variance here, very large variance at the same x level. Here also at the same x level is the age axis. Okay, this the variance is very small. Here the variance is very large. Same thing could be observed, but here we have a negative axis. Here we don't have a negative axis. That's the difference. So practically, when you are doing this, you can either go for this plot or this plot. Doesn't matter. Right? Doesn't matter. You can go for any plot. You don't have to go for both the plots. This is just to explain. You have to check either of these plots. At least, so you have to check one of these plots anyway to see whether the assumptions are met. That's the idea. Same behavior. Presence of outliers. Outliers can be identified from residual plots against the predictor variable or the fitted values. Box plot of residuals. In the box plot, we can identify the residuals. It is more appropriate to use semi-studentized residuals instead of row residuals, since it's become easy to identify residuals that lie many standard deviations from 0. Because we deal this with the MSE, we divide it by the MSE, so the deviations are very low, you can easily identify, right? So it's more appropriate to go with this when you want to identify the outliers. It doesn't say that when you plot the residuals, you cannot identify outliers. But with the scale, right, because the residual is divided by some value, so the scale gets changed, okay? So with the change scale, it is very easy to identify outliers if you plot this one instead of row residuals. Row residuals means the residuals, okay? But still, you should be able to identify residuals from both these plots. Doesn't matter. It's easy and it's very clear enough to identify from this. It's something like this. By looking at the initial scatter plot, still you can simply think about some nonlinearity here, but you are not very sure because it doesn't show much. Okay, one can argue this without any problem. You can fit a linear model for this. One can argue that, right? This is not very severe. But looking at this, the same thing drawn to this plot, you can definitely say this is going to be a nonlinear model. So linear regression model could never be fitted to this if you want to estimate well, right? So something like that. By scatter plot also, you can identify some nonlinearity, but it is not that clearly visible. But when you go to the residual plot, then nonlinearity is clearly visible if it is nonlinear, right? Same idea here. Outlier doesn't say outliers cannot be identified if you plot the residuals against this, but outliers could be clearly identified if you use semi-studentized residuals instead. That's what it says. If the outlier resulted from a mistake or other extraneous effect, always it is recommended to discard. Discarding means we are getting rid of it, right? For example, when you're entering large data set, there could be human errors when you're entering data. Instead of 5, somebody might enter 55. So that can happen. Those things could be clearly identified from these plots. So if you go back again to your data set, whenever you found a residual, you go to the data set and check from your naked eye, because we are humans, we really can understand. Okay, so in case if you found, okay, this is some mistake done by the data entering person, it's always better to omit that observation. You take away that observation from the entire regression analysis. If your sample size is 10, and if you have one outlier which is there by mistake, right? You don't know the initial value, right? If you know the initial value, you can just replace. But if you don't know the initial value, and if you can identify it as an outlier resulted by a mistake, then you make your sample size 9 and refit the regression model. Okay. So when you plot semi-studentized residuals, that is this one, against X, or maybe against fitted values or whatever it is. So if there's one or two things which is very far away from the other observations, you can omit it as you can identify it as a residual, and you can decide whether you are getting rid of it or you are going to estimate it, you are going to reread the value or whatever it is, right? So what I said was, if you plot residuals versus X, sometimes you might not be able to identify this that clearly. What if this get a little bit closer to this one, then you cannot identify it as a residual. So that's what it says. By changing the scale, it is very clear to identify the residuals if there's any. Somebody might say this is also a residual, somebody might not. So because when compared with this one, this could be taken into account, right? We try as much as possible to keep all the data that we have, but if we come up with outliers, and if we cannot do anything, the only possibility is getting rid of that observation, because the data are very important. So in any analysis, we always try to keep all the data as much as possible. At least a single observation is very important. So we have to be very careful. In practice, people who do data entry jobs, they also should be very careful, because the analysis could result high changes, very big changes if you didn't enter data properly. But still, from the diagnostic plots, there is a possibility that you can identify them, but taking off residuals is a waste, right? It's a waste. We value every single observations in our data set. Okay. If you have questions, please ask. Interrupt me and ask. I'm just going through this. Independence of error types. This happens when observations are correlated. That means when observations have relationships, if some observation is depending on the other observation, for example, the rainfall in monthly manner, so that is dependent, right? Say you're doing an experiment, you go to a supermarket, you record data from a person in the morning, right? In the morning, you're recording data from a person. In the afternoon, you're recording data from the other person. In the night, you're recording data from some other person. 3 observations. The next day also, you're doing the same thing. So in that case, there could be a possibility that people who come to the market in the morning behave the same way, almost the same way, rather than the people who come to the market in the night. That is possible, right? Because when you look deeply at it, If it is a weekday, who go to the market in the morning? Most probably the housewives, people who are unemployed. Most probably, I'm not saying it's always, but who go to the market in the night? People who go to work because they don't have time to go to the market while working. They get back home from the office or the workplace and they go to the market. So attitudes, thinking patterns, buying patterns of the customers have some impact on their routine. So they are correlated in that sense, right? Observation on one observation on the first day is correlated with the other observation on the second day, right? And the seasonal effect could be there. If you record data in April or December, that is season, right? The customer feedback would be very different with the discounts, with the seasonal offers that they get. Customer feedback would be very different. So if you're analyzing a data set in that season, you have to stick to that season only. You cannot generalize it to the entire year, right? So within that season, it's okay, but if you're grabbing data all throughout the year, you have to be mindful on that. So when the observations are correlated, if the first person, this also can happen if you're interviewing people in a queue and the second person can hear what the first person says, right? Then again, there is some impact, there is some pattern, because most of the people have gotten used to give the same answer the first person gave because they are not sure of, they're not confident enough to go for another answer. So that really depends. So it's going to be a dependent data set in that case. You should individually interview. So even when collecting data, there's a lot of things that you have to think about. Even when entering data, you have to be extra careful. Statisticians are not the people who always analyze data and give interpretation. No. From the starting point itself, from the designing of experiment stage itself, you have to be very careful. You have to possess a certain set of skills, right? Otherwise, the analysis is going to be useless. So by this, you should be able to understand the entering of data is very important. If you don't have the correct data at hand, you are in trouble at the analysis stage. So that's why most of statistical consulting people, when they're helping the researchers, they say, please come to us, get the consultation at the initial stage itself. Don't collect data and come to us to ask us how to analyze. Don't ever do that, because sometimes the data that you bring in couldn't be done anything. For example, if somebody comes to me with a set of data collected monthly and asks me to do a regression, how can I do? I know the regression is not going to work for that. It's not independent. So that is why if you are not very sure of these techniques, you have to go for a consultant at the beginning. Then the consultant will tell you to in selecting the sample size depending on your problem context. Okay, always a collected data set could not be analyzed that manner, right? You have to be careful from the beginning itself. So that is for your research. Just a small tip for your research, you'd be doing research, right? Most of the time, extended and special degree students. Okay, so yeah. So non-independence of error terms happens when the observations are correlated. This is a common problem for time series data and correlated data. This can be identified graphically via sequence plot of residuals, right? So if you plot the residuals in a timely order, if you see a pattern which is non-random, then of course that's going to be the problem, that the non-independence of observations means non-independence of error terms. That's how you observe it. When the errors are independent, it is expected that the residuals in the sequence plot to fluctuate in more or less random pattern. If it is random, then okay. And the baseline should be 0 anyway. Why the average of errors should be 0? Mean of error should be 0. something like this. So this is just an example, residuals versus X, the time order, right? So if you are getting a line like this, that means this is not random, right? This shows a trend line. This particular thing shows an upward trend. That means with the time, the residual is deviated from zero. Okay, at the beginning also the residual is very high, although it's shown here. If you plot the absolute residuals versus time order, you're getting a plot like this, V-shaped plot, right? Still, the residual is not close to zero, but deviating from zero, and it shows some pattern. Here, if you see a pattern like this, a zigzag-like thing, it's not the zigzag we are talking very something like this. It's not the wiggle shape that we're talking about, but some pattern here. This is non-random, right? It's a cyclical pattern, right? Seasonal effect. If you get the seasonal effect, just like I told you, you're tracking information in April, you're tracking information in non-seasonal month, again you're tracking information in December, you will see something like this, right? Time to time, it changes. Small departures from normality do not create serious problems. So yes, we assume normality, but very small departures from normality is not serious. However, major departures should be of concern, right? You have to do transformations and all that if it is not normal. If it is slightly not normal, you just can ignore that, because it really depends on the sample that you have collected. Box plot. The idea about the symmetry of the residuals and possible outliers can be examined. Have you all seen box plot? Can somebody respond, please? Box plot. Have you seen? It's okay if you have forgotten, but have you seen box plots? Somebody please answer. Yes or no? At least in the chat room if you don't like to speak. Have you seen box plot? I'm not going to ask you questions, just want to get some idea. You should have, but tell me. Somebody please. Yes or no? Have you seen box plots? I want someone of you to answer, please.
I have seen, madam.
Yes, you have seen. Thank you, Image. Okay. So for those who have forgotten, you all can simply search and get this. These are box plots, right? These are box plots. So let's take one and show you. Yeah, so this is sort of a symmetric box plot. So by here, this is the first quantile, this is the third quantile. You can either draw it horizontally or vertically, doesn't matter. This is the median, right? And if everything is symmetric, you can approximate normality here. This is how the distribution is drawn. This is the minimum value, this is the maximum value. If you take this one, the mean median is somewhere here, but here, can you see if you take this range, the median is somewhere here, but the mean is here. So this is very asymmetric. You have a lot of data here from the middle value to the third quantile. So this is asymmetric. This is highly asymmetric. This is slightly normal. For this type of thing, you can say it's slightly normal because this middle line is not in the middle, but neither something like this. Okay. From this type of a box plot, you can identify the outliers. This is an outlying observation, right? So this is the minimum. Actually, here we are taking the maximum value to be this, because this is an extreme value. This is an extreme value. This is an outlier. So if we take this to be the maximum value, everything changes. So looking at the data set, you can see that sometimes in some softwares, they give it by a star. So these are outliers. These can have more than one outlier. So if we take this box plot, we have 3 outliers, right? So yeah, that is the box plot. So the idea about the symmetry of the residual. So you draw the box plot for the residual, and possible outliers could be exact. Histogram. It is helpful detecting the shape of the distribution, whether it is nearly symmetric or skewed. Remember, by the histogram, you cannot say whether it is normal or not, right? Assume you got a symmetric distribution. Can you say it is normal? Why? Because all the normal distributions are symmetric, but not every symmetric distribution is normal. For example, T distribution, that is the only distribution that comes to my head, but there's quite a lot, right? T distribution is also symmetric. It's symmetric around 0. Normal distribution is symmetric around its mean. Standard normal distribution is again a normal type, special type of normal distribution, which is symmetric around 0, right? So it doesn't matter whether it is no, actually, when you get the errors, it should possess a standard normal distribution. Not standard, but the normal distribution, which is symmetric around 0. It's okay to go for a standard normal distribution if the variance is 1. Standard normal means what? Mean 0, variance 1. Okay, so in regression, for the error, actually we don't expect the variance to be 1, but we expect the variance to be constant. So standard normal distribution is just one possibility for the error distribution to be in regression, right? It doesn't have to be the standard normal distribution all the time, saying that the mean is 0, but the mean should be 0. Constant, the variance can be any value, but it doesn't have to be 1 all the time. It can be any value, but mean should be 0. So just by looking at the histogram or any plot, let's say it passes the normal distribution, but still you have to see whether the mean is 0. That is compulsory. But if your residuals are distributed as normal 1, 1, 2, that means mean 1, variance 2. Still you cannot go for that regression model. By the average of errors is around 1, right? So that is not acceptable. So anyway, by a histogram, if you get a histogram like this, so these are basically histograms, right? If you get a histogram like this, it's approximately showing some bell shape, right? This doesn't mean that your error, if this is done for errors, histogram of errors, let's say, this doesn't mean that your errors are normally distributed. It is symmetrically distributed. It is symmetric around some value. It is symmetric around 50, or if this is 0, it's symmetric around 0, whatever it is. You cannot say it is normally distributed. It can be T distributed, right? So this is basically the distribution of T. This is symmetric around 0. This is not normal distribution. So if you plot together, no, these are different T distributions. Okay, so this is something extra, but it's sensible to learn. This is the t distribution, this is the normal distribution. When you take it separately, you cannot distinguish between the two. When you compare, usually t distribution has fat tails. This is the tail. These are the tails of the distribution. This tailing of yourself. This is the body of the distribution. So when it comes to the tail of a t distribution compared to the standard normal, usually t distribution has fatter tails, very fat, heavy tails it has, right? These are very small. But by looking at this thing separately cannot give you any idea. Okay, so that is the comparison. I just want to say that the distribution is also symmetric. So by looking at the histogram, you can say it is either symmetric or skewed, nearly, not perfectly, but still you cannot say whether it is normal or not. It's just giving you some idea about the shape of the distribution. So if you get a sentence like this, by a histogram, you can determine the error terms are normally distributed or not, true or false. It's false. By a histogram, you can detect whether the error terms are symmetric or skewed. Yes, true. So be careful with things like that. I just gave you a clue. Okay, the number of cases in regression should be reasonably large to convey reliable information about the shape of the distribution. That is very, it's something clear, right? Because if you have a histogram with very large boxes, you cannot think of a shape. But if you have a very small, a histogram of like sample size of 1,000, then you can simply get the curve, right? I'll just try to don't worry about the code. I'm just trying to give you some idea. Here I from the normal distribution I got 10 values. Okay, don't worry. From the standard value. Okay, here I'm getting 1,000 values. I'm getting 1,000 values. Okay, now I have two samples, X and T, right? I'm going to get the histogram. I'll just take the histogram in one plane so that you can understand. Don't worry about the code. I'm just showing you. People who do R knows this, but others just watch. I want to have one. This is what I'm talking about, right? Here the sample size is 10, right? Here the sample size is 100. This is just a variable name. It's not t distribution or anything. See, I got these values from a normal distribution. But can you see any normality from this? No, right? It's sort of a skewed distribution. That is basically depending on the data that I generated, right? I got all these 10 observations from a normal distribution, right? Still, by looking at this, you cannot, exactly say, you can, anyway, can't exactly say, but by looking at this, can anybody say this is symmetric or this is a symmetric distribution or normal or whatever? No, right? Because the sample size is very small. But when I increase the sample size to 1,000 or so, you can see the shape, you can observe the shape, right? That is why the meaning of this, the number of cases in regression should be reasonably large to convey reliable information about the shape of the distribution. It should be noticeably large. Otherwise, by looking at the histogram, you can never get an idea about the shape of the distribution, whether it is cubed or whatever it is. We expect a symmetric distribution here, but we don't see such a thing, right? It's not clearly visible. Okay. Normal probability plot. Okay. Each residual is plotted against expected value under normality. A nearly linear plot suggests agreement with normality. So here actually we are getting sort of a diagonal line, and all the points, this is the QQ plot, quantile plot that I'm talking about. We plot the theoretical quantiles and the actual quantiles and the quantiles of the residuals and all that of the data set. And it should go in a diagonal line to approximate normality. That is the normality test, right? People call it normal probability plot. People call it QQ plot, right? So by that, if it shows a linear shape, diagonal shape, you can say the errors are normally distributed. So this is the equation. Don't worry too much about this. This is not tested, right? This thing is not tested, so don't worry. But just to give you some idea on how this really works, okay? Expected value of the kth smallest observation in the random sample of n is approximated by this thing, square root of MSE times. This means this is chi inverse, this thing. Don't worry. So k is the sort of rank, n is the sample size, these are constants. This is the formula. This is the formula of getting this. You don't have to know this formula. This is just for your knowledge, right? Because when it comes to a real data, world data set, when you're analyzing it using some statistical software, the normal probability plot is available. So nobody's going to compute this manually, but I'll show you a code how to compute this manually. So this means the quantile of this, right? Quantile means, let's say you take the normal distribution, what you have, the area under the curve is the probabilities, right? The table value that you read is basically the quantile. Z value of a standard normal distribution is basically the quantile. So by this line, you are getting the quantile, okay? So this is important. This is not important, right? Not important in the sense you don't have to know how to compute this, but I have done a computation just for your knowledge. Other than believing this thing blindly, you can think about it. So residuals versus expected residuals, that is what we got out of this one. So if you are getting, I told you that you have to get a diagonal line sort of. So if you are getting a line like this, a curve like this, that means right skewed, or you call it positively skewed distribution. So it's not a symmetric distribution, which implies that it's never a normal distribution, right? If you are getting something like this, that means it is left skewed. You are plotting the residuals with the expected residuals, right? That is a left skewed or a negatively skewed distribution, so it implies that it's never normal. So symmetrical with heavy tails. If you are getting line like this, so this is basically a line, but when it comes to tails, can you see there is some deviation from the line? So it is symmetric with heavy tails or fat tails, just like T distribution. So you can simply identify if the data are T distributed, then when you plot the QQ plot in tails, you can find something like this. So here there is sort of a linearity. That means the distribution is symmetric, but anyway it's not normal, because I showed you normal distribution has very thin tails. This is an instant where you are getting a T distribution. Distribution is symmetric, but it's not normal, because when it comes to tails, it's very heavy. Okay. So compute expected number residuals of ampules. So this is the air freight brake example, the same example that we were referring to all these days. Under normality, hence obtain the normal probability plot. So this is just for your knowledge. I put a comment here. This will not be tested. So you don't have to know how to do this, right? This will not be tested. I'll just show you what it is, what this is, right? So these are our X values in the air freight brake example. These are our response values. So these are the fitted values, right? Fitted values are gotten from the regression line that we estimated, okay? And when you have the fitted value, when you have the true value, it's just a matter of taking y minus y hat. So 16 minus 14.2 has given you the error. This minus this will give you this. So 9 minus 10.2 is negative 1.2. Likewise, you have gotten nearer terms. Here in ranking, this ranking is a bit special. You have to rank the errors in an ascending order. But for ties, you are just randomly giving values. Anyway, the rank should end up with the sample size. This is a sample with size 10. So the highest rank should be 10. Lowest rank should be 1. Okay. So this is the lowest error. And you put 1 there, right? And this is the next lowest error. Can you see ties here? Negative 1.2 is appearing in 3 places. Usually you put 2 over 3, 2 over 3, 2 over 3. That is the usual way of ranking in non-parametric statistics. Okay. So, but here you just rank it like this. You either can put 2 here, 3 here, and 4 here. Doesn't matter, right? Because when it comes to the plot, it is going to be in the same place. So don't worry. Anyway, this is not tested. I'm just telling you. So this is the next highest value. So you put 2 here, 3, 4. You can arbitrarily select where to put 3, where to put 4, and where to put 2. Fifth one is this one. So this is the next highest error. Likewise, this is the highest error. 1.8 is the highest error. So you put 10 like that. Then how do you compute this? This is the rank, or K in our formula. N is 10 in our case. So the denominator is going to be 10.25. K is going to change from observation to observation. And by MSc, as I remember, it's 2.2. We computed that. So square root of 2.2 multiply by, you are getting some number here. That is a probability value, right? You go to the normal distribution table, the statistical table, standard normal distribution table. You read this probability value, you find this probability value, and you read the contact. You read the Z value, and that particular Z value comes here. That is the idea. Okay. You're getting a probability value here, and you're reading the corresponding quantile value. I think I have the statistical tables. So basically, this is the standard normal table. Assume that you got something like this, 0.6628 here, right? So chi inverse, this means what? 0.42. So that is the Z value that you're reading. Okay. So that is coming from the formula, and you multiply it by the square root of MSE. And you put this. So it's like 10 minus 0.375 divided by 10.25. You are getting a value. You read it from the table, multiply it by square root 2.2, and you are getting this value. So it's, it's a hassle to compute this manually, because if the sample size is 10, you have to check the table 10 times. So it's really hard. So that is why I just did some R code. You don't have to understand this code. I'm just telling you to give you some idea, right? So I record all the values of X here like this as a vector, all these values, and the Y values are recorded like this. And by using R, I'm fitting a regression model. It's just a matter of giving this command. You don't have to learn this. I'm just telling you how I got this. Okay. And you are getting the summary. You get the fitted values. That means by this line, I have gotten the yi hats. Okay. Fitted values. If you run this line, you should be getting this. Shall we check that line by line? Okay, I'm running this line by line. So if I run X, I'm getting these values. Likewise, people who do R know this. So when I get the fitted values, 14.2, 10.2, 18.2, 10.2, these are the fitted values. Shall we just cross check? 14.2, 10.2, 18.2, 10.2, likewise. We have gotten the fitted values by that code line, right? Don't worry. So then I have taken the ANOVA table. It's very easy. And Y, so these observations minus the fitted values, what we got here will give you the residuals. Okay. So if I get the residuals, 1.8, negative 1.22 times 1.8, likewise. 1.8, negative 1.22 times 1.8, likewise, I'm getting the errors. You can compute these things manually, but it's time consuming, so I will just run the R program. So these are the ranks, right? I just got this manually because I have to look and take that. All these ranks are given. And then when computing these, what I have done is, so I have adapted that formula. K minus 0.375 divided by n plus 0.25. So here my sample size is 10. It's going to be 10.25, right? So the ranks are these. When I take the Z values, these are the quantile values that I read from the table, right? If I take this, the values read from these, okay? And then I have gotten the expected score by this formula, square root MSC times the Z value, okay? So n score is square root of MSE times, sorry, these are the probabilities, these are the Z values, normal Z values, standard normal Z values. Right. These are the probability values. I'm sorry. These are the probability values, right? That means these ones, okay? And when I read it from the table, I'm getting the Z values. So that those are these ones. So if you know R, you don't have to read it from the table. You just simply can run this code line. Okay. It's better you all get to know this. Like when you are reading something from the table, you can cross check by using these commands. You can search and see. Then I have plotted these ones with the residuals. Okay, so my Y label is this, X label is this, these are the axis names, and this is my title of the graph. When I plot these, I'm getting things like this. So when ranking, I told you it's okay to arbitrarily select where you put the rank for ties like this, 2, 3, 4. Can you see in this plot you have gotten equal sort of things? So it doesn't matter on how you rank it. Anyway, you have to rank it from 1 to the sample size 10. Right. So here, if this is going in a diagonal line, right? If this is going in a that is all what you have to know. If this is going in a diagonal line, you can approximate normality for residuals, whatever the thing here, right? In R, actually, this is important for the people who do R. Without doing any of these, right? If you know the residuals, right, you can by an inbuilt command you can get it. I think you learned it. This is for special degree students, right? You learned it this Wednesday. QQ norm residuals. You are getting the same thing, right? Normal QQ plot. So this is the plot that we plotted earlier. This plot, right? We are getting the same plot here, right? And we drew a line also. See, so if these things are going in this line, so this is the previous plot. Let me I just want to show that this is the same thing. It's the same plot, right? It's the same plot. Okay, same plot. This is with the line. So whenever you get all these dots approximately aligned in a diagonal line, you can approximate these things to be normally distributed. Okay, so people who do this course, they are expected to know that thing only. If you know this thing properly, that's it. You don't have to worry about these heavy tails or factors or anything. What you have to check is if you are given a diagnostic plot where the theoretical quantiles and the data residuals are plotted, you have to get a diagonal line and that's it. If you are getting a diagonal line, your approximation, your assumption of normality of residuals is obtained. So people who do regression, it's enough to know that fact only, but without blindly believing in these things, you know, it's really good to do some sort of a thing. Why this should be a straight line all the time? Because we are mapping our residuals to the distribution that we really want to have. This could be done to any distribution. Here, actually, we are getting things from the normal distribution, Q norm quantiles from the normal distribution. Normal, actually, the standard normal distribution mean 0, variance 1. We are mapping all these values, the residual values, to the standard normal distribution at each observation so that it should possess a line. If we want to check whether these things possess a binomial distribution, then we have to take the quantiles from the binomial distribution itself, right? I have a nice video for this, so I am not going to play it now. So I uploaded that to the LMS already. Yeah, it's here, video on QQ plot. Okay, so it's basically on this how these are plotted, normal quantiles and data quantiles. So just watch this video, it is very interesting. It explains how pictorially, it explains how these quantiles are taken, like unlike how I explained using the normality table, it partitions the normal distributions and show you how they get the theoretical quantiles, how they met the data quantiles with them. When you watch this video, you would be able to understand why we really expect a straight line, because it's sort of a mapping, right? We are reading the quantile values of, this is our true data set, right? In the sense, these are our residuals, right? This, if we map this to a normal distribution, what's happening, right? If this quantile is the same as this quantile, and if this quantile is same as this quantile, you should be getting a straight line, right? Anyway, if these are if we have 2 points, we are anyway getting a straight line. That line continues if this quantile is same as this quantile. It partitions in a way that the probabilities are equal, so that the quantiles should be equal. So that is why we say if we get a straight line, we are getting the distribution that we assume. So here we are assuming a standard normal distribution, so we take the quantiles, theoretical quantiles out of this. This is not too serious, but just to have some sense on this, I think it's better watching this video. Computing the quantiles is not tested within this course, but without blindly believing what I say, just watch this. It's just 6 to 7 minutes video, so yeah, worth watching it, right? So although it is 11:28, I think we can end up today's lecture. So this is the end. You don't have to worry about this R code or even any of this here onwards, but just make sure you know how to interpret these plots. You might get one of these, or maybe some quantile plot, and ask you questions based on that. So be ready for that. That's it. So to summary, today we learned model diagnostic. After fitting a regression line, why we do model diagnostic is because we really need to know whether the fitted regression line is valid enough to be used for our future estimations, right? As long as we fit a regression line without diagnosing, we never go to use it. Although the R squared value is very high or things like that. Because if the model assumptions like normality, independence of observations, constant variance, things like that are not met, then the model that you got is a lie. You cannot use it. You cannot make predictions from that. So that is the importance of model diagnostic. So we'll meet you in the next lecture with a new chapter. If you have questions, you can stay and ask. Otherwise, you may leave the meeting. Thank you very much for participating to today's lecture. Stay safe.